Hello, Algebra 2 students, and welcome. Today we're going to be talking about section 2.4. Before we actually jump into section 2.4, we're doing something called an exploration, and it's been a second since we've done one of these. But these explorations are going to be really useful in helping us to identify what we're going to be learning during the lesson. So here's what I'd like you to do. I want you to look at exploration 1. I'm going to explain what these questions are asking, and afterwards, I want you to try them for yourself. That's the purpose of these explorations, to see what you can come up with. So, the graph here shows a quadratic function of this form. This is in standard form, right? Which approximates the yearly profits for a company, where PT, our y-axis, is the profit in year T, our x-axis. The first question asks, hey, according to the graph, is this letter A positive, negative, or 0? B is saying to write an expression in terms of this A variable and this B variable that represents the year where they made the least profit. So you should find where they made the least profit and write an expression to show what that value should be. The company made the same yearly profits in 2004 and 2012. Estimate when they made the least profit. And assuming the model is still valid today, are the profits currently increasing, decreasing, or constant? Pause the video, try these out, and come back to unpause after you've done them. And seriously, try these out. Hopefully at this point you've had a chance to try these problems. Let's take a look at them. So, for letter A, it's asking if the value of A should be positive, negative, or 0. Well, that seems ridiculous. How can we decide that based on just this graph? Well, if you remember, in our notes from 2.2, we actually discussed exactly how we determine that. In our parameters section, we said that A is greater than 0, or it's positive, when our graph is facing up like a cup, and it's negative when our graph is down like a frown. And this works for all graphs, including the one that we're doing here. So, if our graph is facing up like a cup, it means our A value should be bigger than 0, since our graph faces up. Question B is very tough, but it helps us to identify what we're looking for. We're trying to find the year, T, when they made the least profit. We're not looking for the amount of profit they made, just the year that it happened. So we're looking for a T value here. And if we look on the graph, we can almost see that the lowest point we've ever reached is right here. If we wanted to draw maybe a vertical dotted line or dashed line, I don't know why we would do that. Crazy, right? If we wanted to draw a line to show what year it would be, it would land right here. What do we call this? What do we call this point, and what do we call the line that goes through it? This is your vertex, and this is your axis of symmetry. Well, we know the formula for the axis of symmetry is x equals negative b over 2a. But we're not dealing with x's in this problem, right? What are we using instead of x? We're using t. Well, the equation that we use to find our axis of symmetry is negative b over 2a. Does that give us an expression in terms of A and B that represents the year T when they made the least profit? I say so. This is the expression they're looking for. They're just looking to see, do you remember how to find the x value of your vertex? Well, question C is telling us that they made the same profit in the years 2004 and 2012. So we want to estimate what year that is. Hang on a second. If they made the same profits in those 2 years, let's pretend like we had a point right over here. let's say this was 2004, 2012 would just be on the other side of the parabola, since a parabola is going to be totally symmetrical. It's the same on both sides. So if you've got a value that equals another one in a parabola, you know they're going to be opposite of each other. We also know that directly in the middle, directly between any two of the same points, is our axis of symmetry. So what's directly halfway between 2004 and 2012? Well, to find that, we can use the formula P plus Q over 2. Normally, P and Q are intercepts, but we can use it here as well to find the middle of our parabola. The reason why we use this for the intercepts is mostly just because the intercepts are where we can guarantee the points will be at the same place. But if they're telling us that we had the same profit in 2004 and 2012, we know they're going to be level when we know the axis of symmetry is going to be halfway between them. So our axis of symmetry is T equals P plus Q over 2. So we can then say T equals 2004 plus 2012 divided by 2. And if I do this in the calculator, 2004 plus 2012 gives us 4016. Dividing by 2 gives us 2008. So we can say with fair certainty the year that made the least profit was 2008. Question D then asks, let's assume the model is still valid today, meaning even after 2012, in 2022, this model still works. Are the profits currently increasing, decreasing, or constant? Well, if we look at our actual graph here, we see that everywhere after the vertex, it's increasing. So it stands to reason that it's going to probably keep increasing, right? We can say that the profits are currently increasing. When T is greater than 2008. So that was the year they made the least profit. Perfect. Next up, we're going to talk about exploration 2, and this one is crucial. This is something that you will actually need to be able to replicate. So the table shows the heights h in feet of a wrench t seconds after it's been dropped. So if we imagine for a second that we've got a wrench, this is going to be my wrench for today. Here's the edge of a building, and we're throwing the wrench off. It's going to fall in a parabola because anything falling, any projectile motion, can be approximated with a parabola. So, what it's saying is this. After 0 seconds, it's at 400 feet. After 1 second, it's at 384. After 2 seconds, at 336, so on. The first thing you want to do is make a scatter plot. So we have to remember how to make a scatter plot. I'm going to show you how we do so. First, we go to Stat, we go to Edit, and we're going to plug in all these points. So I'm going to go 0, 1, 2, 3, 4. In my next column, I'll have those be my y values. We get 400, 384, whoops, that's 34. Try that one again, 384, 336, 256, 144. If you want to make this actually into a scatter plot, you have to make sure your stat plot is on. Otherwise, if I go to graph, nothing is going to show up. You need to go second, stat plot, and make sure that your stat plots are on. Just the first one. When I graph, I still don't see anything, though. It doesn't look anything like the picture we have here. That's because we just need to zoom out to our data. To zoom out, you press the zoom button, and if you want to zoom just to see all of our scatter plot points, to see our statistics, you can go down to zoom stat. It's number 9, zoom stat. Zoom stat will zoom so that you can see our statistics. That looks pretty good, right? What shape does the scatter plot appear to have? Well, we talked about it before. Any projectile, anything you throw or toss, approximately follows a parabola as it does so. So we can say that this is a parabola. And it makes sense, right? It makes sense because as you throw something off a building, it's going to get faster and faster as it drops. It's not going to be falling at a constant rate. That'd be like if it was floating down. You wouldn't imagine throwing something off a building to just go down like an elevator, like at a constant rate. It's going to start off going slow, and it's going to accelerate and go faster and faster and faster until it reaches terminal velocity. We then want to use the quadratic regression feature to find a quadratic model for the data. Huh? Well, we remember doing something called a linear regression in the past. A linear regression, remember, is like our line of best fit. A quadratic regression is similar to a line of best fit, but it best models quadratic relationships, parabolas. Let me show you an example. If I went here and I just went back to my linear regression, and let's say I graphed it on my calculator here. If I graph this, does this line best represent our data? I mean, kind of. Like it's a line that goes through our data points, but it doesn't best represent them. We said the situation would be better with a parabola. So let me clear this, because this doesn't make sense for our type of graph. We want a line that curves with the data. To find a quadratic regression, you're going to go to Stat. You're going to click on the right arrow to go to Calc. And notice that number 5 here, we have quad reg. You're going to click Enter here. And just like before, your x variable is L1, your y variable is L2, you can click Calculate. And you'll see it pops up with a bit of information. First off, it gives you the standard form of a parabola, or of a quadratic, ax squared plus bx plus c. But it also tells you some values for a, b, and c. So it tells us, hey, your a value here should be negative 16. So it should be negative 16 x squared. It tells us that our b value should be 0, so that's plus 0x. And it tells us that our c value should be positive 400. If we simplify this, we will actually get our equation. Well, we know that 0 times x is just 0, so we can say y equals negative 16x squared. We don't need to write down plus 0, but we can write plus 400. That's the equation based on the situation. We have found the equation of a parabola based on a scatter plot. That's what a quadratic regression does. Now, it wants us to graph this quadratic function. And if you just do what I did, if you just click Calculate, nothing happens. We don't see a graph. However, we can still figure this out. Go back to your quadratic regression in Calc, 5 down. So go back to Stat, over to Calc, and go 5 down. But this time, before you click Calculate, we want to store this as a regular equation. That's what store reg EQ is. We want to store it as y1, right? So that we can actually have the equation and graph it. So, I'm going to go down to store reg EQ. I'm going to click on vars button. That's the variables button. I'm going to go to y vars, or y variables. And we'll click enter. I then want to click on y1, and you'll see that now this quadratic regression will go in our spot for y1. If we calculate now and take a look at the y equals menu, you'll see the equation of our graph. And once you have the equation for your graph, if you press graph, it appears. Very, very nice. Now, we want to figure out when this wrench will hit the ground. So let me zoom out just a little bit. In fact, I might need to zoom out a lot. We see here that our graph curves like so down to the ground. And you might be able to figure out where that is, but honestly, it's going to be a little bit tricky to do. Instead, here's my recommendation. You could absolutely go over and pray that it lands right in the middle, but it doesn't. It doesn't land perfectly. See how these values don't actually end up being perfect? That's because the trace function doesn't know what you're looking for. There's two ways to find where the wrench will hit the ground. The first is to go to our table and look for when y is 0. So it hits 0 at -5, when x is -5. But can we have a wrench fall -5 seconds in the past? No. This is called an extraneous solution here, because it doesn't make sense for the problem we have. No, instead, we can go down and we can see, oh, when x is 5, meaning after 5 seconds, y is 0. So it hits the ground after 5 seconds. I also want to show you something you can do to figure it out in a different way. Above the trace button, there's this button that says calc. So you want to go second, calc. We're trying to find what we call a 0. The 0, remember, is where the y value is 0. It's our x-intercepts, basically. To find this, see how our little tracker pops up and it starts blinking? This is going to be very important, so I'm going to zoom in. It asks us to find a left bound. Basically, we have two different places where it hits the x-axis, and the calculator doesn't know which one you want. So you've got to define an area for it to search in. Left bound means, hey, choose some place, basically any place, to the left of the point you're trying to find. So I'm choosing this because it's left to our x-intercept. I click enter, and you'll see a dotted line appears with an arrow. That means the calculator is going to search to the left of this. It also wants a right bound, so we should find a place where the calculator can search to the right of. I'll choose here, why not? Because it's to the right of our point. Notice now we have our area. Now the calculator can guess. If we press enter, bam, it warps over to x equals 5, y equals 0. So it hits the ground after 5 seconds because that's where y is 0. Very nice. 5 seconds because that is where y equals 0. Perfect. If I flip over to the back side of the sheet, we can now begin the actual notes. Now, for these notes, we are going to figure out how to write and solve quadratic equations given some information. We can do this in two different ways. If we're given a point and the vertex, what form of an equation do you think would be helpful here? Vertex form. We have a form that's based around the vertex. We should write an equation in vertex form. Vertex form, as a reminder, goes y equals a times x minus h squared plus k. What is the vertex in vertex form? If we're given a vertex, well, how does that help us? Well, our vertex, as a reminder, is always going to be your h value and your k value. So we can plug in the vertex for h and k. Let me give you an example. Let's say we have this parabola down here. They're giving us the vertex, right? This bottom part is the vertex. So can't we just plug in our vertex? Let's see. if we plug in our vertex, we get y equals a times x minus, our h value is just that x value, so it's going to just be 2, right? Our k value is the y value of our vertex, so we put it as minus 2. Well, everything looks great right now, right? But it's not quite perfect. See, the problem is we have a lot of values, but we do not have an a value here. In order to have an equation, the only two variables remaining should be x and y. This is where the other point comes in. Our point has an x and a y value, right? So to solve this, we plug in vertex for h and k, like we did here, and the point for x and y. Then we can solve for a. It seems weird because in an equation, we want x and y to be left alone. But in order to solve this, we have to temporarily plug those numbers into x and y to see what works. Let's give it a try. So we know that our y value of our point is 6. So we can put a 6 here. 6 equals a times, instead of x minus 2, we know our x value of our point is 4. So this is 4 minus 2 squared. And then, of course, our k value is still minus 2. Whenever you have just one variable alone in an equation, you can solve for that variable. So let's do it. What can we simplify here before we start solving anything? Well, we know that 4 minus 2 is just 2, right? So this is 6 equals a times 2 squared minus 2. Well, hang on a second. We can also simplify 2 squared, right? 2 squared is 4. So this gives us 6 equals 4 times a minus 2. Remember, the a and the 4 are being multiplied together, so you can't just subtract 2 from it. The 4 and the a are being multiplied, so this is 4a minus 2. And now from here, we can just solve like we did in Algebra 1. We want to get a by itself, so what can we do? We start by adding 2 to both sides. These ones cancel out, giving us 8 equals 4a. Well, if we want to solve for a, we should divide both sides by 4, giving us a equals 2, or 2 equals a. If 2 equals a, we now know the missing piece. This is the missing piece of our equation. So now we can just write out our equation, same as we did before up here in this step, but we now know our a value. Y equals, instead of a, we're going to write 2 times x minus 2 squared minus 2. That's the equation. Again, to have your final answer, you want to have x and y be x and y, but everything else should have a number filled in. Let's look up here. Do you think we can do something similar when we're given a point and some x-intercepts? Well, hang on a second. If we're given x-intercepts, what form would be most useful here? We should use intercept form. As a reminder, that's the one that goes y equals a times x minus p times x minus q, where p and q are your x-intercepts. So your x-intercepts here are P0 and Q0. If p is like 3, it'll be x minus 3. If q is like 10, it'll be x minus 10. Those are your intercepts. Just like before, we're going to plug in everything we know to solve for a. So let's plug in the x-intercepts for p and q, because those are what the intercepts are, p and q, and the point that we're given for x and y. Then we can solve for a. Just like the last one, we're trying to solve for the missing piece, the thing that we're not given, the a value. So intercept form looks like a times x minus p times x minus q. And we know that we can plug in p and q as our intercepts. So those are the two pieces of information that we know. Well, what are our intercepts? The first one is negative 4. So this is x minus negative 4 for our first intercept. There we go. And q, our other intercept, we have x minus 6. Remember, these minus signs are only there because that's what the formula is. It's x minus your intercept. But we also are given another point, 1 comma 25. So can we plug those in? We absolutely can. If we plug in the point 125, 25 is the y value. So we get 25 equals a times, what's the x value that we're given? 1. So this is 1 minus negative 4, which we can absolutely simplify to just plus 4 in a minute, times, instead of x, again, we were given the x. We're plugging in 1 again. You'll have to plug in your x of the point twice. But that's 1 minus 6. Now we just simplify and solve for a again. So what is 1 minus negative 4? Well, we know that 1 minus negative 4 is just going to be 1 plus 4. That's just 5. So a times 5 will be the first set of parentheses, times, what's 1 minus 6? Negative 5. 25 equals a times 5 times negative 5. What is 5 times negative 5? We know for a fact that's going to be, I'm going to write it up here since we're running out of space down here, negative 25a. 5 times negative 5 is negative 25. And again, we can solve this using our Algebra 1 skills. We're trying to get a by itself, so we can divide by negative 25 on both sides, since it's negative 25 times a. These ones cancel out, leaving us with just our a value. Our a value equals 25 divided by negative 25. That's just negative 1. So we are good to go. All we need to do now is plug it back in to our equation with the x's and simplify. So we can write this one out as, I'm going to write it up here, y equals, instead of a, we know it's going to be negative 1. So I'm going to write negative, parentheses, x. Instead of minus negative 4, I'm just going to write it as plus 4. So x plus 4 times, I'm really running out of room here, x minus 6. So let me rewrite this over somewhere where there's space. Let me rewrite it right here. Y equals, our a value was negative 1, so we put just negative, or negative 1 if you want to. X plus 4 times x minus 6. And we're done. That's the equation. We have our x's and our y's left blank, so we know we're good. All right, y'all. You can do the same thing in a word problem like this. I want you to see if you can actually figure this one out, this word problem here. Try it for yourself and see if you can figure out how we might be able to find the information. You'll be able to check your answers with me in just a second. But again, we want to write an equation of the parabola, and we'll talk about this one. Pause the video here, try this problem out for yourself using the two strategies we learned up here. So, for our answer here, we end up getting the equation y equals negative 1 over 125 times the quantity x minus 50 squared plus 35. Double check your work to see if you got all this. If not, it may have been that you might have mixed up the placements of your variables here. It's very possible, and it happens all the time, even with me. Or it may have been you're solving here, subtracting 35 from both sides, then dividing by 2,500. Regardless, we're told that they land in a net 90 feet from the cannon, and we now want to figure out what the height of the net is. They're giving us here the horizontal distance in feet from the cannon, right? That's our x value. So what they're saying is, hey, if x was 90, what would y be? What's the height of the net? So we're just plugging in 90 into the equation we just got and solving. Again, pause the video here, see if you can calculate this one out. Come check in just a moment. So, we should have gotten the following. We should have gotten, whoops, sorry, I did that incorrectly. We should have gotten something like 22.2. Our y value equals 22.2. But anytime you're dealing with a word problem, you should write the units as well. In this case, our units are feet. So 22.2 feet tall. That's how high the net is. Let's flip the page and let's talk about the last thing for today. There is some extra practice with these quadratic regressions. If you want to do this page, well, it doesn't have a page number, you can. But I'm flipping over to this one here. We're not going to do this example up top, but again, great practice if you want to practice finding the equations. The last thing we're going to talk about is how to use equations to model data. When data have equally spaced out inputs, meaning our x values go up by the same amount every time, we can analyze the patterns to figure out what type of equation it is. For instance, linear data have what we call constant first differences. What it's saying is, if your x values are constant, your y values should also be changing by a constant amount. As we go from one y value to the next, we should see a pattern of addition or subtraction. That's what it means to be linear. The rate of change is constant. So to get from 10 to 7, we can subtract 3. And 7 to 4 is subtracting 3. And 4 to 1 is subtracting 3. And this is subtracting 3. So we say that this is linear. We say it's linear because the first differences, in other words, the differences between all these y values, or f of x values, because the first differences show a constant rate of change. It's a constant rate of change. But if we look at the quadratic data here, we know it's quadratic because they tell us. Let's take a look and see if it also has constant differences. So to go from 9 to 4, we're subtracting 5, cool beans. From 4 to 1, we're subtracting 3, and immediately we know, oh, it's not linear. The pattern isn't the same. We don't know that it's quadratic yet, but we know that it's not linear for sure. I'm going to complete this pattern and see what happens. So here we subtract 1. To get to positive 1, we add 1 again. To get from 1 to 4, we're adding 3. To get from 4 to 9, we're adding 5. Do we still see a pattern that exists? Well, it's not constant, right? The rate of change isn't constant because it's changing by different numbers every time. But if we compare these numbers, we might actually see some semblance of a pattern. Like, to get from negative 5 to negative 3, for instance, we could just add 2. And to get from negative 3 to negative 1, what can we do? Wait a second, we can add 2 again. And to get from negative 1 to 1, we could add 2. And to get from 1 to 3, we could add 2. And to get from 3 to 5, we can add 2. So what's going on? Linear data has constant first differences. But the first differences were not constant. So what we've checked is the difference between our first differences. The differences between our first differences is called the second difference. The rule is, if your second differences are constant, it's quadratic, meaning it's x squared. Second differences means that it's x squared. Of course, there are other rules for other things too. If you wanted to find the differences between something that was like an x cubed like this, then we could say, oh, okay, it's going to involve us finding the third differences. Or you could find the fourth differences or the fifth differences. It all depends on what type of exponent you're finding. Since we're trying to find a quadratic or x squared, second differences should be constant. All right, everybody, that concludes our 2.4 notes. Thank you so much for listening, and I hope you have a fantastic rest of your day.